Boom. Great. Okay, so ladies and gentlemen, I had asked you to undertake a little exercise at home related to some aspects of monadic use, and that I hoped might help you appreciate some of the material we covered through some interaction. So let's call up this exercise here and talk about it. So what I had suggested was something where you try to create a method, in fact two methods, one called map2 for option and one called map2 for try, that would operate to take an arbitrary function which operates on some values of type t. So you could see it more clearly here, and returns a u. And then it would take two options of type t, two things that might hold a t value or might indicate that they hold nothing. And the results of this would be holding an option u. Okay? I had sought to allow you to undertake this to appreciate the significance of this phenomenon we call lifting. Can anyone describe what lifting is? If we talk about lifting a function to operate on some types of values, what are we speaking of? Anyone? So here's a function that operates on t's. It's a binary function. It takes two t's and returns a u. And I would claim that we're lifting it here to operate on these. And what do I mean by that?
It means you're taking a function that operates on one data type and theoretically making it work on a different data type.
Good. Good. And if we consider possible lifting, let's say lifting for an operator plus, or an operator minus, or an operator concat, or an operator contains. What's the advantage of doing that compared to simply hard coding those sort of operators into, let's say, a thing called option double?
We've generalized it.
We've generalized it. Okay, so you can have an option of t, right? And this is a type parameter, t. And so if we have an option of int, the things that apply to ints, plus, minus, division, are different than the things that apply to, say, an option of string, right? You don't really have division for string, multiplication for string. So by lifting, instead of directly hard coding a method into option of t, we get some extra generality. We can for strings, we can lift operators that operate on strings. For example, concatenate them or return whether or not they one string is contained in another. By contrast, if we lift integer functions into things that are options of ints, we can lift things like plus, minus, divide, etc. So in short, if we have something that's type parameterized, like an option of t, hard coding directly the possible binary operators is really difficult. It's really difficult because we don't know whether it's going to be an option of int, in which case plus, minus, divide applies, or whether it's an option of string, in which case concat, contains, and other operators apply. So if we don't have if we're wanting to use a situation where we have type parameterization, lifting functions to operate on a type parameterized class is really attractive compared to any sort of hard coding. Now, we could create an option of double thing called option double, right? Or optional double. And we can create an optional int. An optional double could have plus minus divided by times. Optional int could have similar things. Optional string would have things related to strings, concat, contains. But as Kurt indicated, we've missed the opportunity to generalize there. We find ourselves writing the same basic mechanisms again and again, just with different types. The logic, the underlying logic, the fact that if you have a none and you try to undertake a binary operator with respect to it, if you have the first element is a logical none, it will return what? What will the result be? It will return, if you have a none as the first element to which you wish to apply a binary operator. What does that always return, regardless whether it's an optional int, an optional double, an optional string?
It returns none.
It returns none.
It doesn't evaluate the function either.
That's right. It doesn't evaluate the function. And if you have a none as the second argument, it will also return none. And if we define each of these classes separately, optional double, optional int, optional string, we lose that generality. We lose the ability to take into account that common substructure, the fact that they differ with respect, they have that in common. I'll be with you in just a second. But we have this option of, instead of hard coding these different things, that you can do a plus and you can do a minus, we can simply lift functions into these data types in option of t, so that anything we have that can operate in int can operate in an option of int. Anything that we have that can operate on a double can operate on an option of double, etc. More than that, we can do so for our own operators, right? I was talking before about plus, minus, divided by. These are standard stock things, very common things. But you may have your own operator that you want to apply. Maybe your operator does something of great interest to you. Maybe it's the nth root of something, or it's a binary operator that represents taking a string and repeating it n times or what have you. The point is, or taking a string and interleaving them. That's a binary operator, and we can lift our arbitrary binary operators or custom designed, custom of interest binary operators into option, and then it can operate on option values. We don't have to custom code. We don't have to, just because we have a binary operator can operate on ints. Now we have to write a special version that operates on options. No, we can simply reuse it by lifting. So Scott, you were going to say something.
I would love to have a function that can take in any value and return, like, it returns none if you can't use that function on what's contained in it. For example, I want to have an option of something, and if the value inside the option is a string and I'm calling multiply on it, it simply returns none.
Right.
Instead of failing.
Well, you can compose that as case, and that is doable.
Yeah, that's true. You can compose it with a case statement, in which case you look at. Yeah, but I think what you're talking about is, does it have a plus function? So maybe plus for string means concat, and plus for int means int. There is a way in Scala to encode what's called structural types or structural type constraints, which basically allow you to do what in Python is called duck typing. Basically, you could say this data type has to support these functions. Now, one important downside of that is that it uses what's called reflection, which is extreme. Yes, cringeworthy it is. And so it's very expensive because it actually has to look up dynamically at runtime. Is this a type that supports it? In contrast, you could say it has to support this interface. Right. It has to implement this value has to implement this interface, in which case that doesn't require reflection at all. That's very performance savvy. But yeah, using structural types is costly.
Yeah. Okay.
Yeah. Anyway, so lifting, ladies and gentlemen, is an attractive feature. It's a very, very attractive feature to be able to lift functions to operate on other types of values rather than declaring them explicitly for that other type of value, declaring their analog for that other type of value. It allows you to reuse your code with a minimum of additional mechanism. Now, one thing I'd ask you to try, please, set your machine upon the surface. There's also a vacated spot here. Okay, so I also asked you to do this for map2 for try.
Is this the one that's due tomorrow?
October 19th.
Exercise 5v5. Online it says it's due tomorrow.
Oops.
Yay!
There was another one. Was there?
Is that
It's take home exercise 5.
5? Yeah.
Yeah.
What?
Okay, but I think on the site it says it's due the 18th. No,
No,
not.
it
No,
says
okay.
due in class 19th.
Well, there is no class on the 19th, so I guess that's
typo
even
is our game.
better. Maybe I'll declare a class tomorrow.
So the type is not bounded.
Yeah, right. So map2 for try, how does that differ from map2 for option? Xiaoyan knows. How does map2 for try, how is that compared to map2 for option?
Well, I think the difference is only the difference between try and option.
That's right.
Yeah.
In the code that you include, is there any difference? The actual body of the body of the code?
Change the option to try. I didn't see.
Sure, that's for the declaration. Yeah, the actual code to carry it out, which involves flat map and which involves map.
No, I'm the same and it works.
Same.
Yeah.
So what this is pointing to, ladies and gentlemen, the fact that the code is the same for both of these is that even though they differ in a certain regard, option and try, they share some deep similarity. And that similarity is related to this concept of a monad that we talked about. They both support flat map and try with similar semantics. And so the code that serves to perform map2 for option is essentially the same as the code that supports map2 for try, as we would say mutatis mutandis, meaning just the inessential things get changed. Yeah, it's basically the same thing except you change option to try. True or not?
Why can't we create a single function that can do it for any monad that we're looking at? That's the opposite. I mean, that's the opposite of what you asked us to do.
Mm-hmm. Mm-hmm.
You know,
So-
in other words, given a value data type,
Well, you
T
could.
there. No, I mean, if it's the same code, we should be able to write it only
You
once.
could with structural types. You could say this needs to take that these values here need to be the same type of a value that supports on the one hand flat map and on the other hand try. So you could in fact put that into place. It would just be expensive because it would require reflection. There's no. Let me sharpen the point.
Mm-hmm.
There's no monad interface which both option and try adhere to, that they implement. If there was an interface, so an interface I'm talking about I'm not talking about an interface in a generic sense. There's a computational construct called an interface,
Right.
and it plays a very important role in Java, and some role in Scala as well. Although
Would this be like a trait?
it's kind of like a trait without implementation in Scala, and ladies and gentlemen, there's not a monadic type to which both of these interface to which both of these adhere or trait. At least I don't think so. Try and option. I don't think they both inherit from from a trait of a common type. There is, however, in Scala a library called higher order kinds,
Yes.
which defines monad, I think, if I'm not mistaken.
In which case, these would be
Though I'd have to.
these would both be monads.
Correct. Well, yes, but they're not declared as such in the standard library. So.
I mean, basically, I would like to write a single function
Yeah.
that says
Oh yeah. Yeah. We're.
map2 for monad,
Yep.
where it has to take in a monad of type T and returns a monad of type U.
Yeah.
I
Yeah.
mean, that's literally what a monad is.
Sure. Sure. Yeah, I
I
agree.
do think these two types are kind of different in the sense of, not in the sense of how they're defined, but more in the sense of what they're supposed to be used. With
Oh, they
options,
are,
You
yeah.
usually want a return of value, but with
Totally.
try, I usually want to do an action, which is quite different, and it's probably a hidden caveat between that lies on the difference between those two things.
Well, but try, you're encapsulating a value as well. I mean, it
Yeah,
does hold
you're
a value.
encapsulating a value, but in most of the cases,
Yeah.
and another kind of a type of use is you want the encapsulating a sort. It's more like you embed the action with it. Like it's basically like the void function. You want to do some act. You want to try whether this thing works or not.
That's true.
You
You
try
ca-
to read from something.
That's true. You can use it with something that returns unit. In other words, it just undertakes an action, doesn't return a value.
right.
But in many cases, that would be try with an option as well,
Yeah, but
because you might not have,
Right,
but it would
the
have a
option is
unit value.
Yeah, but the option is you want to is more focused on you want to get the value, but the try is more on the
Right.
step with actions. Probably you can combine value with it, but I can
Oh,
see
you
that-
certainly can.
Of
I mean,
course you
yeah,
can.
no. Try is used often with a value,
Yeah, you can use value.
but your point is it has other use cases too.
yeah,
Yeah.
You
Fair
can
enough.
just-
Fair enough. Fair enough. But both are monads here. Both serve as monads, and both have this hidden monadic structure. And I think it's a good instinct when you see basically, wait, it's the same code for both. That almost begs you to sort of say, okay, what's the higher order commonality here? The higher commonality is that they are monads, and they both support the same semantics for flat map and try. Now, if this were due half an hour ago, I would show you the code for them. But that I leave as an exercise for you, dear students.
You continue
So,
to leave it as an exercise.
what's that?
You continue to leave it as an exercise.
Indeed, I continue to leave it as an exercise.
You
Per-
have to open your mouth.
And perhaps I wouldn't.
I didn't do it. I forgot.
Perhaps if it's okay with you, we'll discuss it in class Thursday rather than class tomorrow. Okay.
Fair enough.
Now, this was the streams thing. We talked about it. How did you define this factorial function? Hmm? How did you define factorial? Anyone?
So what's the signature here? So I just made it equal to, I made it take in two longs, A and B.
Okay, let's go take a look. Okay, so it took in two longs A and B and did what?
And then it put a stream, and it said the
Okay.
result was A stream concatenated with
Yeah.
factorial stream A times B and B plus 1.
Good. Yeah. Okay. Okay. Good. Anyone else have a different way of doing it? I could show you. I could show you my way.
So one way was mine was zipping the normal stream of starting from 1 to n.
Yeah.
With another factorial stream which starts from 1, and I do append the factorial zip n and map the so it makes tuples of the
Oops.
two streams, and then I can map multiplication over the tuples.
Interesting. Yes, you could do that, can't you?
Yeah.
Yes. Okay, that's really interesting.
I
Congrats.
understand.
So you could do a
Okay.
sliding sort of multiplication.
So it is kind of this is the normal stream of n.
Yeah.
Which starts from 1.
Yeah, that's the
and
from.
by
Yeah,
1.
yeah.
And the other one is from 1 to zipping this n with the factorial, see, in a recursive way.
Yeah.
And mapping the tuples multiplication.
Okay, that's really interesting.
What's
That's
zipping?
zipping is where you combine together. So watch this. Zipping is great.
Oh yeah.
It's great. Okay. So here, array, array 1, 2, 3, right? Array 4, 5, 6, and we're gonna. Okay. Sorry.
Right.
Guess what we're gonna get out? These are the successive pairs, the first with the first, the second with the second, the third with the third. And watch this.
That was one of the questions in this.
Right? So there it only uses the shortest of them, right? Now I wonder, watch this.
Nice.
So remember tuples.
Yeah, they're just
Tuples, sweet.
any.
Tuples can take, things of multiple types, right? Right?
Question, this may sound very basic. Each element in a tuple, though, has to have the same data type. So what I mean is that the first element of each of those tuples has to have the same data type, correct? Or not?
Yeah, because this is an array of pairs of tuples of
Okay.
so pairs
Just wanna make
of,
sure I
of
was
it's a two tuple of int and string. Okay.
It's a two-tuple.
So that's an.
Yeah.
So that's a way to
Two
create a
tuple.
general dictionary.
Yeah. So tuples. I think there's up to 22
Yeah.
element tuples. After that, no more. Something like that. It has, or 23 elements. Yeah, 20 tuples. Yeah.
So
Yeah.
is that 20?
It's called the tuple 2. There's a tuple 3,
Yeah.
and there's a tuple 22, I think. 23, nah.
Why did they choose 22?
Mumble. I don't know. I don't know why they chose 22. But in any case, okay. So this is zipping. So that's really interesting.
So you zipped the from one stream with what's the other stream?
The other string is like factorial, which starts from 1. So you use it in a recursive way. You use it your previously defined factorial, zipping with the first string, and you do a mapping over the
Here's my
tuples.
fact
So it
here.
is multiplication of the.
Interesting.
Yeah, it's really interesting. This is what I did. Generate factorial. Here's mine. So here's n and here's previous fact. This sounds kind of isomorphic to Kurt's,
Similar.
although I think his
Mine's
order
shorter.
of the your names aren't as long as that, right?
But there's fewer things happening also.
Yeah. So here we had, I took the current factorial, which is n times the previous factorial, and that's how the factorials are defined. Factorial of 3 is 3 times factorial of 2, right? And then I returned a string of the current factorial, and then generate factorials of n plus 1 and the current fact. So this second argument is kind of the running.
Right.
The running kind of factorial, the latest factorial. And this is quite a common pattern when you have cogeneration.
Mm-hmm.
So you sort of keep this running state along the way, and you're returning elements that depend on that running state, and the running state determines what element to include, right? So it's kind of keeping track here of n. Yeah, but it's also keeping track of this kind of running state along the way. And it's a little bit similar to how you do factorial recursively, with a tail recursive way, actually, where you sort of pass this along. Okay, so that's a nice way to do it. How about this alternating streams? How did you do that?
Tails of strings.
Sorry?
So you take heads and tails of streams and just you append it
Yeah.
one by one.
That's right, one by one, and you're going to have to alternate, either alternate, A, B, or each time you append two, right? The heads of each, and then you just do it with the tails of each. So you're going to be able to do A, B, and then tail of each. Okay. How about a function that for the primes?
I like this one. This was fun.
Primes?
So all of these it did the same way with like a recursive call.
Yeah. Yeah. So
So I took in just a stream, I guess.
yeah.
And I outputted so the stream comes in from 1, so the first one's or from 0, I guess. So
Okay.
might be from 1, I think, is what I called it.
Okay.
And so the first one's a prime, so you just put that one in the front.
Okay.
And then the next call
Yeah.
takes the tail,
Yeah.
but you filter it.
Okay.
So then I filtered it.
Right.
I basically, every single time I call it, I divide it by the previous, I filter it by the previous head.
Yeah.
So if I've got a list from like 1 to 1, that starts from 1, goes on forever, then it puts 1 on,
Yeah.
and then it's a little bit different though, because I start from 2 in my the stream. So if you've got 1 and 2, but let's say then you look at 3 and you divide 3
Yeah.
by the previous one by 2, and if it's if it's not
that's
filtered,
interesting.
then
Yeah.
it stays around. So then you put 3 on there, and then you go to 4, but you've divided the whole stream by
Right.
2.
Right.
So you've now filtered out all the even numbers.
Right.
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 So then the next part,
Exactly.
you filter out all the multiples of
Exactly.
3.
Exactly. Yeah. Yeah. No, that's really
Interesting.
It was kind of fun.
really nice. I mean, here I did something kind of similar. Oh, nice. 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 Okay. Wow, that's really sweet. That's really sweet.
Same algorithm though.
Nani.
Yeah, okay, here, do you want to project it?
Wow.
Okay, that's beautiful.
Spell.
Do you want to write it on the margin? Or do you want to write it on the board?
I don't think
we
I
project
already
it.
know.
Sorry?
Can you project it?
Yeah, can you
Oh,
project
yeah,
it?
I guess I can.
Cannot.
Yeah.
Okay, let me stop the recording then, because otherwise it will